Come on in. Feel free to ask me questions while we're waiting. We don't have much time. I just barely got here in time. Yeah, thank you, Andrew. Go ahead and everybody, go ahead and type in your first and last name for the role. That'd be great. And like I said, feel free to either chat a question or speak up and let me know if you have any questions on past homework assignments or anything like that. It's pretty much obvious I will not be finishing chapter 14 today, I don't believe. So I've already decided with my face-to-face class that the test on chapters 19 and 20 would potentially could cover 17, 18, 19, and 20. That's an online test, and it's not going to be due on Sunday at 11:59 p.m. like I had originally planned. So I'm definitely at least moving that to Wednesday of next week, which would mean you'd have to have it done by Tuesday at 11:59 p.m. Uh,
You're-
but I haven't decided that yet. I just know it's not going to be Sunday. Go ahead, Jennifer.
Yeah, you're saying 17, 18, 19.
Yeah, the next online test will be 19 and 20, but all my tests are comprehensive, so there's a potential for you to have 17 and 18 in that as well.
Would that be chapters 3 and 4?
Oh, excuse me. Jeez. Thank you.
Thank
Thank
you.
goodness you're here, Jennifer. I was totally telling them about Physics 242. Yes, chapters 3 and 4. I've actually already made that available, but it's not. I'm not going to make it due on Sunday at 11:59 p.m. I'm at least going to push it to Tuesday at 11:59 p.m. Okay. Thanks for correcting me on that. I don't know. I literally just walked in. So, anybody have any questions or corrections they want to let me know that I'm screwing up? uh,
No, I'm good.
Thanks, Andrew. Appreciate that. Thanks for your vote of confidence. All right. Well, we're going to go ahead and get started, folks. I got a couple of specific problems I want to address, so make sure you can have some experience with doing that. A lot of this in the early chapters of physics is not only about physics, where you're learning these equations that we use and the symbols that are in them, so that you can learn specifically what symbols correspond to what concepts and what, actual numbers. Part of that learning of physics is you making that connection that v with a subscript 0 means initial velocity, or v with a subscript I means initial velocity. Force is F, or acceleration's A, speed is often S. Sometimes speed, they will synonymously use it with V, but that's a very weird thing. But anyways, all that kind of stuff is stuff that you will be learning. So I've got to not only introduce that, but I've got to introduce some concepts that you're not that familiar with. Specifically, I want you to be able to understand the difference between mass and weight. Mass is something that is in some sense an intrinsic property, but it's a little different than that. For instance, a human, you could say mass is an intrinsic property, but it's, our mass changes from day to day to day as a result of eating, drinking, and the other end of the stuff. And then there's also, of course, the idea of going from one place to another. That actually introduces the idea of a changing weight. Weight is a force, and it specifically is the attraction of the planet that you're currently on, or the moon that you're currently on. It's the gravitational attraction that that moon or planet has on you. And I'm going to show you that that is a unit of force, and that it actually, of course, can change as the various planets or moons or whatever you're on change. Whereas if we took at one instant and teleported me from planet Earth to the moon, my mass would not change at all. I had to do it teleporting, though, to keep me from sweating out some extra mass or eating some extra mass or anything like that. But my weight would significantly change. In fact, you all know that my weight on on the moon would be about a sixth of my weight on planet Earth. And that's, you're going to see why in a second. Also, there's going to be something called a normal force that a lot of people have a hard time even thinking exists. So, for instance, if you look at a table and you see a desk and you see a book laying on it, you don't really think so much about the table holding up the book, but it clearly is. And the reason why is you sort of think of forces as something that is put out by something that has some agency or something. In other words, it's a thought process that makes you put out a force. But to be honest with you, once you build something to stand in a particular position and a specific orientation, anything you do to sit something on top of that is going to require that thing to put a force on it to keep it from falling. So that's what we got to introduce, and it's called the normal force, and it's called normal not because it's the opposite of abnormal, but specifically because the mathematical term for perpendicular to a plane is called normal as opposed to perpendicular. Okay, so we're going to learn that normal force. As time goes on, of course, we're also going to learn about friction forces and stuff like that. But right now, we just have to get some things out of the way. Another part of what's going on in these early chapters is teaching you mathematical techniques that'll be used over and over again. And for instance, I'm going to show you the tried and true way of solving the Atwood machine. There's a very specific way of solving a system of equations, and any way will work to solve a system of equations, but one just jumps out at us very obviously when we're doing this problem. And then there's another problem, like if you hang fuzzy dice from your rearview mirror, there's a very easy way of solving that system of equations. And if I don't give it to you, you might not see it because it's very different from what methods you'd learn in your pre-calculus or high school algebra 1 or 2 courses. So let's go ahead and get started. I will reiterate what I told you last time, which is that there's Newton came up with 3 laws of motion. And as I've warned you before, whenever you're taking a course and it has a chapter called, blank, blank, blank laws, blank, 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 you should all automatically think, oh, well, that could possibly come up as a question in a later test. And that's the truth. If something says blatantly law, as a heading for a chapter, or has a very specific name that's a whole chapter or maybe covers multiple chapters, that's a pretty big concept. So you might as well commit it to memory. And by that, I mean, I'm going to give you Newton's 3 laws of motion, and I'm going to give them to you in a way that you can memorize. And not only do you need to know those definitions, but you also need to know what their title is. So it's not enough to just know Newton's first law, second law, and third law. You've got to know which one is the first law, which one's the second law, which one's the third law. When we get to gravity, that's going to include Kepler's laws of planetary motion and Newton's law of gravity. So Kepler has 3 laws of planetary motion. You should know which the first is, what the second is, and what the third is. You should know Newton's law of gravity, Newton's first law, Newton's second law, Newton's third law. So just keep that in mind, because that could pop up at any point, anywhere. And that's supposed to be like us teachers would say, hey, this is just a chucker question that I can throw in there and it'll give all my students, 5 or 10 points. So keep that in mind. So let's go ahead and get started. I'm going to tell you the first law. So the first law is very much what Galileo figured out. So Galileo, after being threatened a little bit with torture in his Inquisition trial, and then being sentenced to in-house arrest. Actually, he was sentenced to life in prison, more or less. But Barberini, who had become Pope Urban VIII, Barberini was the cardinal's name before he became a pope. Hopefully, y'all have noticed that over time, that a person comes into office with a actual name that they use their whole life, and then like Cardinal Ratzinger became the previous pope. And I can't remember what pope he was called now, but anyways, if anybody remembers, by all means, let us know. So this Barberini person was a cardinal, and then when he became pope, he took the name, the ecclesiastical name, I think is what they call it, Pope Urban VIII, so VIII. But luckily, that guy was a close personal friend of his, and we think that probably Barberini decided to let him live out his sentence in in-house arrest, and a local cardinal or local church figure was the one that sort of oversaw that arrest. And in fact, that guy was a friend of Galileo's as well. So he actually encouraged Galileo to publish some more stuff, only he was forbidden to publish anything about the heavens and specifically the models of the universe. You can look into the Vatican. The Vatican actually has some of the transcripts. It has all sorts of stuff that you can look at there to see how that story went down. They more or less got him on a technicality. Specifically, they said he was told specific things he was allowed to do and specific things he was not allowed to do. He ended up doing some of the things he was not allowed to do. However, this list that they brought before them was the only document that they brought before anybody that didn't have all the signatures on it. Specifically, it didn't have Galileo's signature on it. So it seemed a little questionable at best. But anyways, he goes to his home and decides that, yeah, I can't study astronomy, or what we would call astronomy. I can't study the planet's motion and stuff like that anymore. And I can't write about that. But one thing he knew for a fact is that every model of the universe that existed at that time had Jupiter moving. And what we know for a fact was, unlike what we were worried about, specifically like a bird sitting on a tree limb seeing a worm down by the ground, if the bird lifted off the tree limb to fly down to get the actual worm, then if the planet Earth was actually orbiting around the sun, there's a chance that the Earth would leave the bird behind. That was one of the major concerns about how we couldn't necessarily say the Earth was orbiting the sun, specifically because things would be left behind, and we did not think of that as a type of motion that could happen. However, when Galileo spotted what we now call the Galilean moons, what he called the Medicean moons, Io, Europa, Ganymede, and Callisto, everybody agreed Jupiter was moving, and therefore we had 4 satellites of the planet Jupiter that constantly attended and orbited around Jupiter. So that was clearly a case that contradicted the bird and the worm scenario. So he decided he needed to understand motion, and he started to study motion as falling objects, but he realized he didn't have a good enough timepiece. So he had to take falling objects and translate them to objects rolling down an inclined plane, a very gradual inclined plane. And then he could use the components of the acceleration, vertical and horizontal, which makes the angled acceleration. The vertical component would basically be the gravitational acceleration that we now know of as 9.8 meters per second every second. And he was able to get that from it. And in so doing, he had to come up with his own clock, and he used a clock where you'd basically, if you wanted to time something, you open up a stopcock on a valve of a vat of water, that would begin to fill up another container of water. And then when the time stopped, you close the stopcock, and that would stop the water flowing. And then you could weigh the water. And you didn't necessarily know how much time it was, but what you knew is if that water weighed 3 kilograms, say, and another vat of water from a previous experiment only weighed 1 kilogram, then you know whatever resulted in the 3 kilograms took 3 times as long. Okay, so that was pretty smart idea. Anyways, what he reached, the conclusion he reached, in addition to more or less being responsible for the definition of constant velocity, the definition of velocity, I would say they didn't have a difference necessarily between velocity and speed, because vectors were not invented until roughly the 1830 era, somewhere around there. So they didn't have any concept of vectors, but he did come up with an idea of what constant velocity or constant speed was, and what acceleration was, and specifically what constant acceleration was. So constant speed he defined as any motion in which a given distance was traveled every time interval. So if you chose your time interval to be 1/10 of a second, and you found in one time interval of 1/10 of a second an object moved 3 meters, if you then found every other 1/10 of a second that it was moving, it moved another 3 meters, then you'd know that that was constant velocity. That velocity, of course, would be 3 meters divided by 1/10 of a second, so that'd be 30 meters per second. He then said acceleration, constant acceleration specifically, is going to be a type of motion where the change in speed is the same for a given time interval. So if you used a second, or if you used 1/10 of a second, or if you used 100th of a second, doesn't really matter. Whatever you use, the change in speed would be the same for every one of those intervals. So if you said, for instance, 1 second is the time interval, what we'd find is gravity causes the speed of an object to change by 9.8 meters per second every second. So if you could cut out air resistance and drop something from a very, very high height above the earth, then what you'd find out is in the first whole second, it would go from 0 to 9.8. That'd be a change in velocity of 9.8 meters per second. And then from 1 second to 2 seconds would be another 1 second interval. It'd go from 9.8 to 19.6, so on and so forth. So that's what he came up with. Ultimately, what he decided was by looking at inclined planes and realizing that when something went up an inclined plane, it tended to slow down. When something went down an inclined plane, it tended to speed up. So he argued that if the plane was perfectly level, it would neither speed up nor slow down. He also imagined a scenario where he actually did this. He would take and allow a ball to roll down one side of like you can picture a half pipe like we use in skateboarding and bike riding and stuff like that. You could imagine a ball rolling down and then coming up to some height over here. And what he noticed is it looked like the ball was trying to get up to the same height on the other side, but he noticed him skidding and bumping and stuff like that. So he'd go and sand the pseudo half pipe design to make sure it's extra smooth, polish it really well. And then he found that the ball would come even closer to getting back to the same height that the ball initially had. And he'd, fine tune it again with some more polishing and sanding, and it'd get even closer still. So then he argued, what if the other half of that half pipe was very gradual? The ball would have to roll a really, really long distance before it would ever get back to its original height. So he argued that obviously if it was perfectly flat, it would run forever. And that made him reach the conclusion that there is some quantity called inertia that makes an object reluctant to change its speed and direction. And that is essentially Galileo's law of inertia, is that an object's not going to change its speed or its direction unless a force acts upon it. Newton comes along, and again, as I told you before, he said, as I've seen further than others is only because I stood on the shoulders of giants. In this case, he really is right, because he's really just borrowing from Galileo when he said that an object in motion tends to stay in that state of motion unless acted upon by a net external force. So an object in motion tends to stay in that state of motion unless acted upon by a net external force. Now that we have the language of vectors, I can go ahead and tell you that a shorter way of saying that is an object will maintain a constant velocity unless acted upon by a net external force. And remember, velocity is the vector quantity that has not only a magnitude, which is like its speed, but it also has a direction. So what we're saying is neither the speed nor the direction will change of an object, even if that speed and direction is 0, okay, meaning it's 0 meters per second or whatever. It's not going to change unless a net external force is acting on it. External, meaning that you can't apply a force to yourself. No matter what, Andrew Jackson telling us about lifting ourselves up by our bootstraps, you can't actually do that. You can't apply a force to yourself to make yourself accelerate. So that's not going to happen. So you've got to make sure you're talking about forces that are acting on the object that are not as a result of other parts of the object. Okay. So that's what we mean by external. When I say net, that's sort of like your net pay. You multiply the number of hours you work times your hourly rate, and then you say plus commission, say, minus FICA, minus this, minus that, minus this. And you do all this adding and addition and subtraction and stuff like that until you get your net pay. That's what you do with the forces too. You got to take all the external forces acting on a body, and you've got to add them as vectors, meaning they have, X components, Y components, Z components, all that stuff. You got to add the like components to get the new X component, add the like components to get the new Y component, add the like components to get the new Z component, and then you have a new total force. That's what we mean by the net force. So the net external force really is a sum of all the forces, and it has to be all the forces acting on the body from some other object. Okay. As we are doing this, though, we're going to use Newton's second law. And as a guideline for you, Newton's second law says, you're probably familiar with the form F equals ma. I'm going to say sigma F equals ma, because sigmas are assigned for summation, and that reminds you to sum up all the forces acting on it. So that's important thing for you to do. So when you go to account for all the forces to make sure that you're not missing any, what you want to think is, what are all the things physically touching the object whose acceleration you might be interested in knowing? Okay. Everything that touches it has the potential to put a force on it. And then you got to say, okay, well, there are some weird forces that actually can be applied to an object without touching it. Those forces are gravity, the electric force, the magnetic force, and that's pretty much it. Okay. We're not learning yet about the nuclear forces, so you can leave out those two. But right now it's gravity, the electric force, and the magnetic force. Those are the only forces that can apply force to something without physically touching it. Okay. So we've got Newton's first law. An object in motion tends to stay in that state of motion unless acted upon by a net external force, which I said we can say more succinctly by saying an object will maintain a constant velocity unless acted upon by a net external force. The Newton's second law says that an object's acceleration is directly proportional to. So we do the thumbs up, thumbs up. I'm going to show you in equation form what that means in a second. But evidently, that's a celebratory thing to stick up two thumbs at once, thanks to Zoom. So thumbs up means if you double the sum of all the forces, if you double that total force, then you're going to double the acceleration. Now, if the total force had an exponent of 2 or 3 or something like that on it, then it would be different. But the law of Newton's law of physics, the second law of motion, doesn't have an exponent, so it's just 1 to 1. So that means if the force goes up by a factor of 2.37, the acceleration goes up by a factor of 2.37. It's also inversely proportional to the mass. So if the mass goes up by a factor of 3, then the acceleration goes down by a factor of 3. Again, no exponent on it other than 1. So if the mass goes up by a factor of 3, the acceleration goes down by a factor of 3. If the mass goes down by a factor of 2, the acceleration goes up by a factor of 2. So that's Newton's second law, and it actually gives you some information that allows us to figure out the direction as well, and therefore you can make it a vector equation. Specifically, the acceleration occurs in exactly the same direction as the net force. So when you add up all the forces vectorially, you end up getting a vector force that has a magnitude and direction, and what we're telling you is the acceleration will be exactly parallel to that force. Okay? So that's Newton's second law. Newton's third law is normally stated for every action, there's equal but opposite reaction, which is sort of helpful, but not that great. Okay. I once saw a book. I want to say it was called, or someone read it to me. It was called Physics for Art Majors or something like that. And in that book, it said, you can't touch without being touched. That was that was their explanation of Newton's third law. I don't like that one. It's a little touchy, cheesy kind of thing there. So touchy-feely stuff. I'm not into that. But anyways, I will write it in equation form. And what I'll tell you is that the force on object A due to object B, I would normally call the F vector with a subscript A, B, meaning the force on object A as a result of object B. And if I wish to use that terminology, then Newton's third law would say the force on object A as a result of object B is a vector equal to the negative of the vector, the force on object B as a result of object A. So if you change the order of the subscripts, then you have to change the sign to a negative. And of course, that's a vector equation. So it tells you both things. It tells you that the magnitudes would be equal, but the directions would be opposite. Okay. So those are Newton's three laws. You can even use, for instance, that third law as a way to explain something like, have you ever tried to hit really hard a fly in the air? It's not easy. In fact, it's so hard that if you're just using your hand, you almost will never be able to kill a fly with your hand unless you squish it against something. But if you just hit it in the air, pop, like that, it's going to turn out that it doesn't get hurt too terribly much. And one way you can look at that is through Newton's third law, where basically you're saying, hey, I would like to hit this fly really, really hard. But guess what? I can only put as big a force on the fly as the fly can put back on me. That's what Newton's third law says. Now, that's a little wishy-washy and doesn't tell you all the ins and outs of it. So let me explain it a little bit more in detail. Remember, Newton's second law says the sum of all the forces is equal to the object's mass times its acceleration. So if you really wanted to hit a fly really, really, really hard, what's going to happen is you're going to have to move your hand really, really fast. And then as you hit it, it's going to take that fly, which, best case scenario for the fly is it happens to be sitting still in the air, not moving at all. Okay. And then you hit it, and it's going to have to, in a short period of time, go from 0 speed to whatever speed your hand has. Well, that's okay. That's an acceleration. And we know that acceleration is directly proportional to the force and inversely proportional to the mass. So to get a large acceleration, you're going to have to use a large force. But guess what? You also, because the actual mass is so small, you're automatically going to get a really big acceleration without much of a force. So it takes such a small force to get the fly to go from 0 meters per second or 0 miles per hour to even 90 miles per hour if you happen to be like a professional baseball pitcher and you're doing it with your baseball pitching motion, and you can throw a 90-mile fastball. If that's 90-mile-per-hour fastball. If that's the case, then you are going to bring that fly up to 90 miles per hour, and it's going to be in a short period of time. But the fly was so infinitesimally light that it really didn't matter. Okay, so that's the longer explanation of how Newton's third law says it's really hard to hit a fly. Okay, other things you can do is like Newton's first law says an object in motion tends to stay in that state of motion unless acted upon by a net external force. You can do some logical things like that with that and conclude that, for instance, if an object does not continue with a constant velocity, then clearly a force must be on it, and stuff like that. So that's kind of handy. Either way, let's go ahead and get started now that I've given you an intro to Newton's laws of motion. I highly recommend you looking into your textbook and reading it thoroughly on these chapters so that you can get a deeper understanding of these things and the concepts. Specifically, look for misconceptual questions that your book has in its chapters and try to make as much sense of them as you can. And of course, I also assign the homework, the conceptual homework assignment. So that's another thing you can do to make sure you're learning the concepts. We don't get to spend quite as much time just doing concepts and demos in the calculus-based physics course as I would like. So I'm going ahead and sharing the screen of my iPad with you guys. And what you'll see right now is a table. And what I have is a table that is supposed to be a breakdown of the units within the various system of units that we use in physics. The systems of units that we use in physics is, in fact, there's 3 systems to some extent. There's the British imperial system, which Great Britain had, but Great Britain does not use anymore. Okay. In fact, it's us and Burma/Myanmar. We're the only 2 countries that still use the British system. And in the British system, there is a quantity known as mass, and the units in that system are the slug. So that's the actual unit of mass in the British system is the slug. And then there's the concept of weight, which is a force, and that unit in the British system is the pound. Now, that being said, engineers are kind of have done a lot of things and have made a lot of things more convenient for themselves, at least in the sense of more convenient without changing units. Okay. So despite the fact that the entire Earth uses units other than us, except for us in Myanmar, is a really good reason for us to consider not using those units anymore. But here we are. Okay. That hasn't been tried since basically since Jimmy Carter, and that's before all y'all were born. So we're probably not going to get a change anytime soon. But in an attempt to make it as convenient as possible, they've introduced the unit of the pound mass and the unit of the pound force. So you can, in principle, still say a pound is a unit of mass, but it's some weird bastardized version of the original pound that was made up specifically so it didn't seem as weird as it was. Okay. There's also the CGS system, which before everybody got on board with the SI system, the System International, which is also called the MKS system, we were using the CGS system. And that CGS means centimeter gram second, just like MKS means meter kilogram second. And the unit for mass in the CGS system is the gram, and the unit for force is the dyne. DYN is the abbreviation. Okay. In the MKS system that we use, the unit of mass is the kilogram, and the unit of force is the Newton. So just to give you some background, for instance, one slug is 32.17 pounds roughly, which is also about 14.594 kilograms. Also, one dyne is 10 to the negative fifth newtons. In other words, it's 100,000th of a newton. The reason why is, remember, a dyne, that can come from Newton's second law, F equals ma, and the F has to have the units of the dyne or the newton. The M has to have the unit of the system, and the A has to have the unit of the system. So if you're looking in the CGS unit, then you're looking at a unit of mass that's in grams instead of kilograms, and you're looking at a unit for acceleration that's in centimeters per second instead of meters per second. You know, for instance, 9.80 meters per second every second is the acceleration of gravity, but in centimeters per second, it's 980. And a kilogram is 1,000 grams. So you can see you're off by a factor of 100 by using 980 instead of 9.8. And you see that you're off by another factor of 1,000 by using grams instead of kilograms. Sure enough, if you multiply 1,000 times 100, you get 100,000. That's why a dyne is 100,000th, TH on the end of that, of a Newton. Okay. Any questions on that? Now, remember also, the weight is really the affinity of gravity for the object. And the gravity is caused by the big ginormous body that it's on, unless it's not on a big ginormous body. So for instance, if you looked at one of the satellites we sent to land on asteroids, those asteroids aren't huge, but they still have a gravitational force. And that gravitational force, being that they're so small, is way smaller. But still, you can see, for instance, photographs and videos where we've actually parked crafts on asteroids and they stayed there with the minimal amount of gravity it had. Okay. So let's start off by making sense of the term weight. How do we get it? And that sort of thing. So I'm going to imagine an object in free fall, as we studied in chapter 2 and then later in chapter 3 as well. So if an object's in free fall, what we mean by that is it's falling without air resistance and only under the force of gravity. Okay. Can anybody tell me of a word that starts with W that represents the force of gravity on a person or a thing?
Weight.
There you go. That's it. So what I'm going to do is I'm going to draw an object. Its mass will be M, and I'm going to imagine it having a force acting on it. And as you said, that force is going to be the weight W. Since it's in free fall, that's the total force. Okay, because what we said in free fall is there's no air resistance. The only force acting on it is gravity. So we're going to apply Newton's second law, and Newton's second law is, I told you I would tell you how I write it. So I write that with that Greek symbol, capital sigma that you see there, F is equal to M times A. And of course, I put the vector symbols on it. And if you solve that for A, then you can get what I was telling you about earlier. The summation of the forces is in the numerator and the mass is in the denominator. And of course, there's no fraction on the left, so you can write this as A over 1. And you see that A and the sum of all the forces are both in the numerator, so they're thumbs up, thumbs up. Whereas the A and the M are also on opposite sides of the equal, but they're also on opposite sides of the fraction bar, so they're thumbs up, thumbs down. So remember, that's a refresher of what that means. So now that we know Newton's second law, the summation of the forces has got to be the object's mass times the object's acceleration. And we already know that all the forces is just the weight. So the left-hand side is just going to become weight. Now the right-hand side is going to become mass times acceleration. Can anybody tell me on planet Earth what is the acceleration in free fall?
9.8 meters per
9.8.
second squared.
Yeah, the 9.8 meters per second every second, what we call G, in other words, right? So I'm going to use G just because you'll know that, oh, that's the gravitational acceleration. So if I go to some other planet, I'll know to use the gravitational acceleration there. So I'm just going to put G as the acceleration over here. And guess what? We now have an equation for weight. So that's how you calculate weight. So for instance, if you're thinking about a toddler, say, that weighs 10 kilograms, then that's the toddler's mass, not its weight. And if you wanted to know the toddler's weight, then you would report that in newtons, and that would be 98.0 newtons. So a 10 kilogram toddler implies a 98.0 Newton toddler. Does that make sense? Because all you do is just take the mass and you multiply it by G, and that gives you your that gives you your weight. Any questions on that one? Okay. So another thing that we have to make sense of is the idea of a table. As a table or an inanimate object providing a force. So as I told you before, there's going to be a force that we're going to use over and over, and it's called the normal force. And the normal force, your book will sometimes call it N. I never use N as the symbol. I usually say F sub N is the force. Okay, either one of those are acceptable. But the main thing is that it means a force perpendicular to the surface on which the object sits. Oops. So for instance, if you had a table sitting like this, okay, and you put an object on it here like this, and its mass is, let's say, big M, then a free body diagram is what we'd want to draw to analyze it. So this is a free body diagram. What we would do is draw the mass as if it's just a point particle. And then what we would see is that there is a force acting on this, and it's in the downward direction, which I'm going to assume is negative. So I'll draw that force as red, and the force is going to be the object's weight, mg. Now, what I'm doing is I'm imagining a coordinate system in which that's the positive y direction, and maybe this is the positive x direction. Okay. Now, if you look at that free body diagram, that's where you immediately discover, oh, wow, according to Newton's first law, an object in motion tends to stay in that state of motion unless acted upon by a net external force. We see that this object has a velocity 0 and the velocity remains 0. Because of that, we know that the net force must be 0. So I'm obviously missing something from my free body diagram. Does that make sense to everyone? And because of that, and I should probably make this force a little smaller because it's not going to be able to equilibrate otherwise. So I will do this and say this is mg. So it turns out, since Newton's first law says an object in motion tends to stay in that state of motion unless acted upon by an external force, this book or whatever it is sitting on top of that table is not changing its velocity. So the net force must be 0. So there must be another force, that at least one other force, that's completely canceling this one out. And as far as we know about vectors, that means it has to have exactly the same magnitude and point in the opposite direction. So I'm going to say this force is that, and I'm going to call that F sub n the normal force. Okay, so that's what your normal force is. You have to reach the conclusion that it exists no matter what. If it bothers you to think about an inanimate object putting a force on something, just imagine an elephant sitting on a table. If you imagine an elephant, but you started off with imagining a toddler or maybe an infant first, and then a toddler, and then a young child, and then a teenager, and then a grown-up, and then fat Mr. Younger, and then an elephant. Okay. Eventually you get to the point where the table collapsed because the force was too large. And the fact that the individual objects were held up until you got to too large of a force tells you that there clearly was some force there. So does everybody have an idea what the normal force is? Does that make some sense? Okay. So to be honest with you, the first thing I want to do is I'm going to solve a little more advanced problem because that's what you guys are doing in lab. So I think it might be helpful to go ahead and jump into that. So I'm going to introduce you to the Atwood machine. And it has a bunch of different flavors. Okay. The simplest version of the Atwood machine is what I'm drawing here. And what I mean by that is we're going to imagine a massless, frictionless pulley. So this is a massless, whoa, Nelly. This is a massless, frictionless, whoa. Evidently, I forgot that there's no I before R in frictionless. Now, later we can get rid of these requirements of it being a massless, frictionless pulley. And right now, you're probably rightly saying there's no such thing as a massless, frictionless pulley. And you're absolutely right. But from a mathematical standpoint, and therefore from a physics standpoint, you can get as close to a massless, frictionless pulley as you wish by just reducing the mass and the friction to a small fraction of the forces involved. So for instance, if you had a 20-pound mass hanging on one side of the pulley and a 10-pound mass hanging on the other side of the pulley, then the force differential there is about 10 pounds. Okay. So if you take that number 10 pounds and divide it by 10, then that's sort of the bare minimum of, or let's say that's sort of the maximum size or mass or weight of the pulley that it could actually have to be negligible. Ideally, you'd like to take that 10 pounds and divide it by 100 or 1,000 or 10,000. But as long as it's at least a factor of 10 smaller, there is some freedom for you to assume that to be massless. Same thing with the friction. It's a friction force. turns out to be on the order of 1/10 of the size of the fourth or even smaller, then you're probably okay with that. So keep the pragmatist alive in you and realize that no, there is no massless pulley. No, there is no frictionless world, but we can always achieve as close to it as we want by just successively getting heavier and heavier objects to compare it with, or trying to reduce the friction or the mass in whatever way we can. So we're going to have a massless pulley. And in addition to the massless pulley, I'm going to hang a really large mass here. And I'm going to represent it as a really large mass by saying its mass is big M. Ooh. Okay. And now to further iterate that its mass is super big and what we're doing, I'm going to draw another string over here on this side, and way down here, I'm going to put a wee little mass. And that wee little mass is lowercase m. Okay. So what this diagram is just yelling to you is that clearly a huge mass is hanging up really, really high. And if you allowed the pulley to rotate freely, or you took whatever forces are holding this in its state that it's currently in, immediately what would happen is the mass big M would begin to fall downward, and the mass little m would be yanked upward. Okay, that looks like what this diagram is telling me, and I'm going to use that as a definition of a coordinate direction. So I'm going to say that and you can use the y-axis, the x-axis, the z-axis, doesn't really matter. And just to show you that, I'm going to say, let's say the x-axis points up on the left-hand side. So I'm going to draw a free body diagram for the little mass, little m, and I'm going to imagine the positive x direction is pointing up, because when the little mass goes up, that's consistent with the big mass going down, which is what I think is going to happen. Now, another thing I'll tell you is you can find places on the internet where they will say, you can treat this as one big object and its mass is m plus m, right? I'm going to tell you, don't do that. Okay. You can, and there's ways you can do it to keep you from making mistakes. But in general, it's way easier to make mistakes if you do that. Now, there will be a time where you can do that in addition to what I'm going to do, and that's fine too. But what I'm going to recommend you do is you create a free body diagram for each of the masses that are doing the moving. Okay. So I'm going to start off by drawing a free body diagram for lowercase m. So here's my lowercase m's free body diagram. And if you were like in that box, what you'd say is, okay, I feel like I'm sitting here in this box and everything's cool, but there's a rope attached to the top of my box. And I know darn good well, if they drop that big box over there, it's going to yank me up really high. So according to the people in the box and the box itself, it's as if there's some force associated with that rope or string that's pulling me up. Whenever we have a rope or a chain or a string or something like that, we call that force a tension. Some books will call it F sub T to recommend, to let you know that it's a force, but it's specifically a tension type. I usually just use the symbol T. Now, I'm also going to go ahead and say that I've chosen a coordinate system, and my coordinate system has the positive x direction up. Even though up is normally associated with y or maybe z, it's okay. It doesn't matter. You can use any coordinates you want. So now I'm going to draw this positive force in the upward direction, and that positive force is going to be blue because it's in the upward direction. So sometimes I try to use like blue for positive and red for negative, but this force is going to be called T, the tension. You might think, hey, shouldn't we call that like T sub L because it's on the left side? Well, what I'm going to show you in a little bit is that there's no way the tension on the little m is going to be different from the tension on the big M. They're going to have the same magnitude, so there's no need in subscripting it. Now, in addition to the tension pulling the mass up, what's keeping the mass from just taking off upward at G, gravitational acceleration? Anybody? I got my two students with faces, and one's looking out in the window off to his right flank, and the other one, she's got a blur around her. She's not doing anything. I think her son's coming in, and he may or may not be wearing a Star Trek uniform. So anybody tell me what force is preventing that tension from yanking that mass up at an acceleration of g? Is there anything touching m from below? No. So that leaves only the other kind of force that I warned you about. Remember, when you're making free body diagrams, you have to imagine everything that's touching the object could provide a force. We've already covered that one instance. And then we have to imagine forces like gravity and the electric force and the magnetic force and the strong nuclear force and the weak nuclear force.
I was gonna say gravity, but weight, I think is.
Exactly. Weight would be the better word, but yeah, it's absolutely a result of gravity. So yes, and since it's in the negative direction, I'm going to draw it with a red arrow, and its magnitude is mg. Okay. Now that I have a free body diagram, I can write Newton's second law, and that is the summation of the forces in the x direction is equal to mass times acceleration in the x direction. So when I write Newton's second law in that vector form, I can make that three separate equations. The summation of forces in the x direction equals mass times acceleration in the x direction. The summation of forces in the y direction is equal to mass times acceleration in the y direction. And the summation of forces in the z direction equals mass times acceleration in the z direction. Just remember, you can always do that. Later, you'll also learn other coordinates, but that's good enough for right now. Now, the big thing about the sigma is looks like or sounds like an S. Okay, sigma. That's because it's a sum, and technically what we're doing is adding all the forces. But since we're doing this in one dimension, the vectorness of these forces is just handled by it being either positive or negative. So what we're really doing on the left-hand side is adding all the forces, though sometimes it will look like subtraction. I just want to point that out for now, so you'll know from now to the rest of the semester and next semester. Okay. So the T is pointing in the positive direction, so I'm going to call that a positive force. I'm going to say T, and then normally what we'd have to write is plus, and then I'd write negative mg. You can see that would be boring and suck, and it would make me have to write it over and over, and I don't want to do any of that. So I'm just going to write it as minus mg. Now, here's one of the perks of doing a free body diagram per object. There's no other mass in this free body diagram, so I know exactly what goes on the right-hand side. It's the lowercase m, and I'm not even going to subscript the a. I'm just going to call it a, and now I'm going to tell you why. So does everybody agree with that statement of Newton's first law of motion, or Newton's second law of motion for the little m? That makes sense to everyone? Okay. So imagine this. We're going to go on the assumption that the rope, string, or chain, or whatever this is going over the pulley is not going to get slack, and it's also not going to stretch. It's not like an elastic string or anything like that. Okay. So if I were to take the little bit of string right above big M and I pulled it down 1 inch, what would happen to the string on the left-hand side? Go for it, Andrew. If I pulled downward on the little string right above the big M and I pulled it down 1 inch, what would happen to the string on the left-hand side right above the little m?
It would also.
I mean, I know it'd obviously be lifted up, but
Would it be exactly an inch?
well, yes, it would have lifted up an inch.
Yep, exactly. So what that tells us is the displacement of big M is the same as the displacement of little m, right? If big M moved down by 1 inch, then little m is going to move up by 1 inch. And what I said is we're going to try to keep that consistent, or else we'll have to make up a new equation to relate the displacement of little m with the displacement of big M by putting a negative sign between them or something weird like that. So when you see me draw the other coordinate and then the other free body diagram, you'll see that I handle that way. Now, what if instead of just pulling the string down on the right by 1 inch, what if I pulled the string on the right down by 1 inch and I did so in 1 second? What would happen to the string on the left? Would you say the same thing would happen to it? It would go up by 1 inch in 1 second?
Yeah, it's
Yeah.
the same.
Yeah. So what that tells us is the velocity should be the same. Now, if I took the string on the right-hand side and I pulled it down 1 inch in the first second and then 2 inches in the second, the same thing would happen to the string on the left. It would go up 1 inch in the first second. It would go up 2 inches in the second. So from that, we can see that the velocity, which was 1 meter per or 1 inch per second in the first second and 2 inches per second in the second, that's an acceleration, and the two accelerations must be equal. So I don't need to write A left or A right or A1 or A2 or A big M or A little m. I just write A because the accelerations are going to be the same. Does that make sense to everyone now? Okay, so that's some of the logic that has to go into this stuff. But once you've had it explained to you, you shouldn't, I mean, you should think of it every time until you feel comfortable with it. And then just forget about it and just know it if you need it. Okay. So now I'm going to draw another free body diagram. This time I'm going to draw it for the mass big M. So here's my mass big M. And remember, I said anything consistent with big M going down and little m going up is going to be my positive direction. So I'm going to call the coordinate system for big M as positive X pointing down. Notice that's what pulleys do, right? On the left-hand side, we had X pointing up, but if you go around the pulley, then you see that it's pointing down on the right-hand side. So that should be consistent with that and make you feel okay. Everybody cool with that? Okay. Now, according to big M, it's going to be pulled downward by the Earth's gravitational pull. So its weight is big mg. Now, according to big M, or maybe the people in a box that's represented by big M, they would have plummeted at 9.8 meters per second every second if it wasn't for that stupid rope back there slowing them down and of course, saving their life. So now what we're going to say is there's a force that's tending to slow it down, pointing in the opposite direction. And that force I'm going to call just plain T. And notice I use the exact same symbol as I used on the other side. Here's the reason for that. Let's imagine for a second that that pulley was not massless. If I were to pull down on the mass M or pull down on the rope above mass M, then that rope would actually cause the pulley to rotate. And since the pulley had mass, it would take a bit of force to do that. And it would also be lifting the mass little m up. That would take an additional force to lift it. Okay. Now, if you go to the other side of the pulley and just below where the pulley is, grab the rope and lift up, you would see that you only have to lift the mass little m. So if that pulley were massive, then the tension on the right-hand side would be different than the tension on the left. Does that make sense to everyone? So that's the difference. Now, also, if instead of it being having mass, let's assume it is massless, but it has friction. Do you see the same thing would happen again? I would have to apply a force to the string on the right that not only lifts mass M, but also fights the friction in the pulley. So the tension on the left would again be a little smaller because its job is only to lift up mass M, whereas the tension on the right would be to lift up mass M and to fight the friction in the pulley. That makes sense? So that's why the two tensions are the same. When we introduce a massive pulley or a frictionful pulley, then we're going to have a T left and a T right, and that means two unknowns instead of one. Now we've got two unknowns already, the T, tension, and A, the acceleration that both objects will get. I'm going to go ahead and draw a free body diagram for big M. Write out Newton's second law for big M. So Newton's second law says the sum of all the forces is equal to mass times acceleration, and we're only concerned about it in the x direction, so I put the subscripts on it. Now, remember, we're actually adding these forces, but mg points in the positive direction, so I'm going to say mg, and normally we'd say plus because the sigma means adding up forces. But this T is pointing in the negative direction, so it has a negative direction associated with it. So you'd end up writing plus a minus T. I don't want to write that, so I'm going to write minus T. And again, there's no ambiguity what mass to use, so I'm going to write big M times A, and this is going to be called equation 2. So I did tell you a big part of physics is learning not only what the symbols are and what conceptually they correspond to, but also learning some mathematical tricks. This is not a mathematical trick you're not familiar with. It's just one you might not have thought of in this context, okay? When I see equation 1 and equation 2, I immediately think a really smart idea would be add equation 1 to equation 2. The reason why is T is an unknown, and it's positive in one equation and negative in the other. So if you add the two equations together, you're going to eliminate T, which is an unknown. And that's, you know, the lion's share of the battle when you're trying to solve a system of two equations, two unknowns. Notice also, if I hadn't made the arrangement where the positive x direction is up on the left and down on the right, I'd have two different accelerations or something like that, and I'd actually have to then make up a third equation to relate the two accelerations to each other. So that's why I consistently make those x's being positive in a consistent direction. So make sure you do that. So we're going to add equation 1 and 2. So add equations 1 and 2. And I apologize, I don't know what that N is, but that definitely looks like a third grade girl's N. So, and I don't even know what that means at this point, but I know a third grade girl should not be writing like me. That's all I know. Okay. So when I add number 1 and number 2, I'm going to add the left side to the left side and the right side to the right side. So I'll write out more than I would normally write just so you'll see what I'm getting. I'm getting T minus lowercase mg plus uppercase mg minus T is equal to lowercase ma plus uppercase ma. So you can see now that minus T and plus T cancels each other out. That's the whole reason I did that. And that's what you should do every time you go to solve an Atwood machine. Is you're going to find two of the variables are going to have an opposite sign, and you should probably subtract them. In cases later, when we're actually having massive pulleys, it'll be like a TL minus TR, and they're not the same anymore, but subtracting them will still come in handy. Now that I have that, I'm also going to make use of the fact that there's a common factor of G and a common factor of A in the two sides. So I'm going to write the left-hand side as M. I'm going to write it with black for starters. I'm going to write it as big M minus little m parenthesis G is equal to little m plus big M parenthesis A. And now I can solve for A and say that A is going to be M minus M over M plus big M, all of that in parentheses. Notice the numerator is kilograms minus kilograms, which gives you kilograms. The denominator is kilograms plus kilograms, which gives you kilograms. If you divide the numerator by the denominator, you get no units. So this quantity right here has no units, but I do have a G outside. So this is sort of an ideal scenario for the way you want to solve symbolically an equation in physics. Is you have the thing on the left, which in this case is an acceleration. So if we made it clear that the acceleration equation I give you is clearly in the appropriate units, you feel a little bit more confident about it. And that's what we've done. We've made it a dimensionless quantity, m minus m over m plus m, times something whose units are clearly the same as the units of acceleration, specifically g. So that's our first answer. So we now know the acceleration of the Atwood machine. So that would be like part A, where, you know, part A is find the acceleration, part B is find the tension. Everybody follow what we did there? Okay. So now that I have that, I'm free to take that A and put it in equation 1 or equation 2 and then solve for T. Well, in equation 1, the T is already positive, so I'm going to use that so I don't have a chance of dropping a negative by mistake. So I'm going to call this, well, I'll say A. So plug A into 1. So this is going to be T minus mg is equal to m times m minus m over m plus m times g. I'm going to get the t by itself on the left by adding mg to both sides. So I'm going to say plus mg plus m minus m squared over m plus m, all that times g. Okay. Now what I'm going to do is I'm going to get a common denominator between the two terms. So I'm going to multiply the lowercase m times g by m plus m over m plus m. That's going to give me m times m plus m over m plus m. And notice there's a common factor of g in both terms. So I'm just going to go ahead and pull that outside completely. And this is going to be m minus m squared over m plus m times g. Now I can distribute that. And distributing that m, I get m squared plus m plus m minus m squared over m plus m, all that times g. You can see now that the m squared cancels out with the negative m squared, and these two terms just become 2m. I'm going to write it a little differently. I'm going to say T is equal to 2m over m plus m times big MG. Do you see that the 2m over m plus m has no units? And T is a unit of force, or is a force. And wouldn't you agree that mg has the units of force? Okay, so that is, again, another ideal way of writing a symbolic solution. I'm going to call this B. But now we've solved the Atwood machine. When you do your lab, I don't think you've done the Atwood machine yet in linear graphing 1. You're going to have a mass hanging on one side, a mass hanging on the other side. And what you're supposed to do is take like a 5-gram mass off of one of them and move it to the other one. By doing that, the M plus M in the bottom stays the same, but you're changing the M minus M by basically 10 grams if you move 5 grams. And then you can plot, of course, M minus M times G on the horizontal axis and V on the vertical axis, and the slope would actually be the acceleration, which is, well, you could find the slope not necessarily being the acceleration, but it'd be 1 over M plus M. So that's going to come in handy. Anybody have any questions on that? All right. Now, this Atwood machine can change a bunch of different ways. We can, instead of having the mass little m hang straight down, I could put that pulley at the end of a right triangle and then have the rope hanging on, coming off the pulley and running parallel to the hypotenuse of the triangle, and then little mass little m sitting on the hypotenuse and big M hanging off the edge of the thing. So then we'd have an Atwood machine that has part of it on an incline. We could then have an Atwood machine where both parts are on inclines and they're at different angles. Then we could add friction on each of the inclines and all sorts of stuff. So this is not going to be a problem that goes away, in other words. Let me try another problem that's a little, hopefully a little more understandable and a little bit more teachable, I should say. So let's imagine for a second that I have a mass of, let's say, 5.00 kilograms. It's attached by a rope to a mass that is 10.00 kilograms, and it's attached by a rope to a mass that is 15.00 kilograms. And finally, one more mass that has a mass of 20.00 kilograms. And let's say I'm pulling it with a force equal to, and I'm going to say this whole thing is on a frictionless surface. Okay. Let's say this force is 150.0 newtons to the right. What I want to know is, what is the acceleration? What is T1? What is T2? And what is T3? So this is fairly instructive because what you're going to see is I can, like I told you earlier, there is a way where I can treat this whole thing as one mass. And in this case, this is something you sort of have to do to figure out the total acceleration. You can do it initially or you can do it at the end. I'm going to do it at the end here. So the first thing I'm going to do is I'm going to draw a free body diagram for the first mass. And that free body diagram is going to have an x-axis that points this way. And I'm going to have a mass of 5.00 kilograms there. Now, it will have a normal force acting on it and a mg acting on it, but those two are just going to cancel each other out, so I'm not even going to bother with it. However, and actually I should have written it this way. I should have wrote this one is mg and the other one is that, and then I could make the axis, of course, black. Now, what I also have is a tension pulling in the positive x direction, and that's called tension T1. Okay, so the summation of the forces in the y direction equals mass times acceleration in y direction. We're just pulling this along, so there's no reason for these things to be jumping up and down. So the acceleration in the y direction is really going to be 0. This is the only time I'm going to write the y one, just so you'd know what it looks like, though. So what I end up getting is F normal, which is in the positive direction, minus 5.00 kilograms times 9.80 meters per second every second is equal to 0. And you can see that that just tells you the normal force is basically 5 times 9.8 newtons. But the summation of the forces in the x direction is equal to mass times acceleration in the x direction is basically just T1 is equal to 5.00 kilograms times A. And I'm going to call that equation 1. Now I'm going to do the same thing for the second mass. So here's my x-axis. I'm going to ignore y from here on out, okay, everybody? So I'm going to put a mass here, and it's going to be 10.00 kilograms. And what I'm going to see is I have a, here's another student coming in. I have a tension T2 pulling it to the right, but I also have a tension T1 pulling it to the left. Does that make sense to everyone? Obviously that T1's pulling the 5 ahead, but it's dragging on the 10 kilogram one. That makes sense? All right, now the summation of the forces in the x direction equals mass times acceleration in the x direction. So this is going to give me T2 minus T1 is equal to 10.00 kilograms times A, and that's going to be equation 2. I'm going to do the next one as well. There's my x-axis. There's my 15.00 kilograms. And I'm going to have a force of T3 pulling to the left and a force of T2 pulling to the right. Again, we're ignoring the y component because that just allows us to solve for the normal force. But notice it is every time just the weight, as long as the force is level and there's no other vertical forces on it. So now in this one, I'm going to get the summation. Oops, use a different color. The summation of the forces in the x direction equals mass times acceleration in the x direction. This is going to give me T3 minus T2 is equal to 15.00 kilograms times A, and that's going to be equation 3. I can do one more, which is all we need. And this time it's going to be a 20.00 kilogram mass. It's going to have a force of 150.0 newtons. And it's also going to have a force of T3 newtons. So in this case, the summation of the forces in the x direction equals mass times acceleration in the x direction is going to give us 150.0 newtons minus T3 is equal to 20.00 kilograms times A. And that'll be equation 4. I obviously ran out of space, but I think y'all can make out what that is. Okay. Actually, let me just write it again. It's aggravating me. I only got a couple minutes left. We can, of course, now solve this system this way, and it'll be nice and neat. What I'm going to do is I'm going to write 150.0 newtons minus T3 is equal to 20.00 kilograms times A, and that's going to be equation 4. Okay. So what I can do in principle is I can treat the whole system as a big block. So let's look at this real quick. I'm going to say, here's a blob of matter. The matter is 20 plus 15 is 35, plus 10 is 45, plus 5 is 50. So I'm going to say a 50.00 kilogram mass has a force of 150.0 newtons acting on it. Therefore, Newton's second law, the summation of forces in the x direction equals mass times acceleration in the x direction, gives me 150.0 newtons is equal to 50.00. That's one extra sig fig, by the way, times A. So now I can get that clearly A is 150.0 newtons divided by 50.00 kilograms. So you end up getting 3.00 meters per second every second is the acceleration. And that was really nice. But by doing it that way, we've completely eliminated the chances of figuring out the tensions. But now that we have the tension, now that we have the acceleration, we can go ahead and plug that in 4 to get T3. Once we have T3, we can plug that in A in equation 3 and solve for T2. Then plug in T2 and A in equation 2 and solve for T2, solve for T1, and then we're done. Okay, so I'll leave it to you guys to solve for the tensions. And then, of course, all the equations have to be valid. So if you plug those in after you get the tensions and they don't all equal like they're supposed to, then you'll know you made a mistake. I will have it done. In fact, I'll probably do it and just put the answers in the back of this. But you guys are all free to go. Remember, I am not finished with chapter 4, so your test is not due Sunday at 11:59 p.m. I'm going to push that at least till Tuesday at 11:59 p.m. You have a good weekend. Stay safe. Text or email me if you have any questions, and have a safe weekend. And you're free to go. I'm going to wait for the last person to leave in case anybody has any questions. Don't forget to text or to chat me your first and last name. Yeah, Jen.
I just want to make sure you're talking about the online test, right? Not the face-to-face.
Yes, the online. The face-to-face is at least the second week of October, if not the third week. So, okay.
All right, there's time. Thank you.
All right. See you, Jen.
All right. See ya. Thank you.
You're welcome.
Have a good afternoon.
You too. See ya.
So I had one question.
Uh-huh.
For T, is that's the force on the rope, correct?
Yeah, T is what we call a tension.
Yeah, that's what I thought. I was just making sure.
Yep, that's it. Your book will call it F with a subscript T a lot of times, or some other things like that. I always call it just T.
Yeah. And what I was looking at, I get how you're doing the diagram where you have the T2 minus T1 because one's in the left direction and one's in the right.
Right.
But I feel like, at least in my mind, the farther you go forward, it should have more tension on the rope because you're pulling the weight of all the ones behind it.
Right. So you'd expect like T3 to be much higher than T2, for instance.
But I would expect it to be addition, like because you're adding the weight of the block behind it, which, but it's because the second rope is taking some of that tension.
Yeah, and that's notice that equation 3, for instance, has T3 minus T2. That's exactly how that's taken into account. So your leanings are right. It is really addition, and it's coming through by doing bit by bit equation 4, then equation 3, and then equation 2, and then equation 1.
Okay. Okay, I see.
It's just if you did it the way you were talking about, you wouldn't necessarily be able to figure out anything but T3. You couldn't figure out T2 or T1.
I
But
got
by doing it this way, it allows me to figure out all of them.
Yeah, okay. It's just it's a little slightly different from the way we did it with the trig based.
All
Uh,
right.
they just taught it slightly different because we went from basically the basics of the W equals MA and then the MG and all that. Then we went into like the incline, uh,
Gotcha.
where you had to worry about, which direction everything was pointing and all that stuff. I don't know if we ever did like consecutive weights attached. It was more so like if you stack them together on a beam or something and you had to determine like the distribution um and all that. So I wasn't sure how the
Gotcha. Whatever you use in the algebra-based course should still work here. So if you felt more comfortable doing it that way, that shouldn't be a problem. If you want me to double check it just to make sure, feel free to work this out any way you want and let me look at it, and I'll tell you whether it's done properly or not. I have no problem with that.
Okay, yeah, when I'm doing some of the practice stuff, I may if some of it looks a little different than I'm used to, I may end up like sending you a message or something
No problem.
just to make sure like the way if I do notice it is any different, just to make sure it does still apply.
Gotcha.
um,
No problem. Anybody have any other questions yourself, or anybody else have any questions?
I think that was all I had. If I do find another one or something, I will message you or something.
All right, sounds good.
Have a good weekend.
You too. Take care. Hey, Mark, you have a question for me?
Yeah, it's about the homework again. It's the energy in capacitors and electric field.
Right.
And I'm having trouble for everything that's happening after part B. So like the problem is basically trying to like find the right formula. Like, do you mind if I share my screen?
Yes, let me make sure it's set so that you can. Yes, you can now.
So yeah, so far I just been like trying to like find the right formula.
Okay. Are you doing this one on the right hand, the left-hand side?
Yes, this is the homework, and this is a Desmos calculator I'm just using.
Gotcha. What's the question that they're asking for over here on this left-hand side? I can't. Okay. See if I can zoom in on that. There you go. A parallel plate capacitor is connected to a battery. The energy of the capacitor is U0. The capacitor remains connected to the battery with the plates, while the plates are slowly pulled apart until the separation doubles. The new energy of the capacitor is U. Find the ratio of U over U0. Okay. So when they told you the capacitor remains connected to the battery, that means the V is going to stay the same.
Uh-huh.
The charge can change though. So you want to use one of the versions, 1/2 CV squared or any of those other versions for the energy.
1/2 CVs.
And since you're also going to change the plate separation, you definitely need one of the equations that has the C in it, because you're going to substitute for that epsilon 0 A over D, or at least C over 2, because when you double the plate separation, since C is equal to epsilon 0 A over D, you're going to cut the new capacitance down by a factor of 2.
Okay, so you use a formula that has V in it. So 1/2 or C over V squared, or 1/2 Q times V is good.
Which one did you use? What was that again?
The formula I'm using is, I think it was C over V square. Yeah,
Okay,
this one. I'm using this formula right now. So C times V square over 2.
I got you.
And for the bottom, I just used this formula. So it was something like this. CV square over 2 divided by this, which is QV, divided by 2.
Hmm.
And then I multiply the top with the bottom. So basically 2 times QV. Then I get rid of this. And then since still V here, I get rid of this. And would it look something like this?
So the U, that should be, that's the new capacitor, right? U0 is supposed to be the original capacitor.
Yep, U0 is the original capacitor. So I use the formula U equal QV divided by 2. Wait, would that be the right formula now I think about it?
Let me give you an idea how to look at this. Let me share borrow your screen for a second.
Okay.
Okay, so I'm going to share screen. Okay. So as you know, the potential energy of a capacitor, or the energy stored in a capacitor, could be 1/2 CV squared. That's the
Yes.
one I just remember because it looks just like 1/2 KX squared, but it also looks a little bit like 1/2 MV squared for kinetic energy. But the other forms we could use are Q squared over 2C, or we could also use QV over 2. The main thing is that with the battery connected, that implies V0 is equal to V. In other words, it stays constant. So U0 is the energy of it before we do anything. And since the V is going to stay constant, but the Q could change, I'm going to choose to use Q squared over 2C. So I'm going to say the original charge is Q0 and the original capacitance is C0. I will also say that the new the new energy is the new charge Q squared over 2 times the new capacitance. But the new capacitance, since C is equal to epsilon 0 A over D, that is what the original capacitance is. That means the new capacitance should be epsilon 0 A0 over D over 2. They did say cut it in half, right? Or did they say double it?
I believe you say double.
I think you might be right.
Yes, slowly pull apart into the plate separation doubles.
Thank you, doubled. Yeah, thanks for catching that. So this is now going to be divided by 2D0. So you see that that's exactly C0 over 2. Does that make sense?
Oh, wait, I'm writing this down. So Q square equal 2C. What does it say? But right there, or L R O T? It's below the word battery. It's the cursive.
Yeah, so the battery connected means it keeps the voltage constant, but because it's connected, charge can go back into the battery or more charge can come out of the battery.
Okay, but I'm talking about the word in cursive, the cursive letter. The
Gotcha.
L R OT or something?
Well, what I have to do now is I already have U0. That's just in terms of C0 and Q0. I've figured out what the new C is. It's C0 over 2. But now I got to figure out what the Q is as well.
Mhm.
And the way we're going to do that, do you know what equation we need to use to figure out what's happened to Q?
Define Q. It would be
I did this in class, but it might not ring a bell to you right now. Remember, the definition of capacitance is that C is equal to Q over V, always.
oh, so it'd be Q times CV.
Exactly. So Q is equal to C times V is another way of looking at it. So you could say Q0 is clearly equal to basically C0 times V0. However, the new Q is equal to the new C times the same V0.
Because battery didn't change or voltage didn't change.
Yeah, because the battery keeps the voltage from changing. Now, the new capacitance, of course, is already C0 over 2. So we get C0 over 2 times V0 over 2, which is equal to 1/2 C0 V0. So you see that this is Q0 over 2.
Wait, hold on, let me finish writing them all down first.
No problem.
Mu C is equal to sigma naught times original area times 2 times distance original, which is equal to C 0 over 2, and C is equal to Q V equal Q 0 equals C 0 V 0, and new Q is equal to new C times V original equals C original divided by 2 times original voltage and
Do you follow what I did there, Mark?
kinda.
So what we had to do was we had to use one of the formulas for the energy. And I showed you those three, 1/2 CV squared. That one had the V in it, so that wasn't very useful because I know the Q and the C are going to change. I had Q squared over 2C. That one has Q and C, so that's a good one. QV over 2, that one has V in it. That's not going to change, and it doesn't give me a chance to change the C. So that's why I ended up using Q squared over 2C. If we just go on the
Because-
assumption that initially the charge is Q0 and the capacitance is C0, then U0 is just Q0 squared over 2C0 as we get right here. Does that make sense?
Yeah, so right there, you say the original potential energy is equal to Q square original times 2C original.
I'm right. Now we use the same formula for the new one, but instead of a sub-zero, we just use a Q and a C. But we got to figure out what Q is, and we got to figure out what C is. What I did first was figure out what C is because I know C0 for a parallel plate capacitor is just epsilon 0 A0 over D0.
Mhm.
Now, according to the problem, it said you're going to slowly separate the plates to twice as big a distance. So I changed the distance from D0 to 2D0.
Yep.
And notice the epsilon 0 A0 over D0 is still the original C0. And therefore, I can just write it as C0 over 2. Does that make sense?
Okay, so that's how you got C0, because C is equal to epsilon over A divided by distance.
Exactly. So now you see how I got C0 over 2 in
Uh-huh.
this expression.
Yes, I see that one now.
Okay. Now the other thing was we had to figure out the charge. So I used the definition of capacitance, which is capacitance is equal to charge per unit voltage.
Mhm.
Again, using sub-zeros to represent the original values, I can solve this for Q and say Q0 is equal to C0 times V0.
Yep.
But V0 and V are the same. They're not going to change at all. So I can now do the same thing for the new capacitance configuration where Q is going to be C times V. Now it would really be C times V, but V0 and V are the same thing. So that's why I was able to write the V0 there. Does that make sense?
Mhm.
Then all I have to do is plug in my answer for what C is, which is C0 over 2. So that's how I got C0 over 2 times V0.
Yep.
Now I could just pull that 2 in front and call that 1/2, and I get C0 V0, which you can see is exactly Q0. So I wrote Q0 over 2 is the new charge.
Yep.
So now I use the formula U is Q squared over 2C, but I know Q is Q0 over 2, so I put that in parentheses and square it. And I also know C is C0 over 2, so I put that down here in the bottom.
Wait, why didn't you use C? Oh, wait. Wait, no, never mind.
You see where that was already part of the formula.
Yeah.
So those 2's in the bottom cancel out, but when you square this parentheses up here, it's going to turn that 2 into a 4.
Mhm.
So now all I need to do is take U and divide it by U0, which is what I'm doing here.
Okay, so I think I get what you're saying.
So all I do is I put this quantity down here. Oops, I put it the opposite way. Glad I looked over this. I actually put it upside down. I don't know why I did, but I did. So let me kill this real quick. And that was making some me feel a little bit weird because it wasn't supposed to be that. So this is going to be Q0 squared
Over 4C
G0.
original.
And then the U0 was Q0 squared over 2, excuse me, over 2C0. So now I can see this C0 is going to cancel out with that C0, and this Q0 squared is going to cancel out with this Q0 squared. And then I'm going to get all that's left in the numerator is 1/4, and all that's left in the denominator is 1/2. And division by a fraction is the same thing as multiplication by the reciprocal. So I'm going to say 2, excuse me, 2/1. Okay. So now what you see is the answer is 2/4, which is 1/2. Good thing I caught that because I was getting ready to tell you to put 2 in there. It's supposed to be 1/2, not 2.
Yeah, so that is the answer. Alright, so part D is basically the same as part C, except the capacitor is disconnected. So charge would remain the same then, right?
Yep.
Alright, so we can do that later, I guess.
So I
Part-
assume you have another problem where they're saying you're keeping the battery, instead of keeping it connected, you're going to disconnect it.
Yes, part D is the capacitor is then disconnected from the battery.
So this time the Q can't change, but the V can. So you don't want to use, for instance, this one because it's got a Q in it, or this one because it's got a Q in it. You want to use this
So yeah, that
because
one.
both C and V will change.
So that means so the original potential energy would be U0 equal 1/2 times what's the formula again? CV square, I think. CV square. Yeah, CV square. And we need to find the new voltage would be U equal 1/2 C. Right. Yeah. And does it double or yes, they are pulled apart into separation double, so we need to find the new charge. So C0 is equal to sigma naught of original A over original D, and the new C will be sigma naught over original A times 2D original, making the new C equal to original C over 2. And now we need to find C, and C is equal to Q over V. And we know Q is going to stay the same no matter what. So that would mean right. So we're looking for C, yeah, so that means And to find v, it is. Let's see, how do I find v? Okay, that's all. So v equal q original times nu c, and nu c is equal to co divided by 2. Just that's the initial value. C initial divided by 2. I messed up, but that's why. That it for this step?
I got 2 for that one. Is that what you got?
I wasn't done yet, but isn't the charge one? Because it say that when it's separate, it doubles. But it looks like you are, unless I'm reading that wrong.
So did you see the argument I made there? U0, since the C and the V are going to change, we want to use the 1/2 CV squared formula.
Yes.
So U0 should be 1/2 C0 V0 squared.
Hmm. Yep.
Then I define C0 to be epsilon 0 A0 over D0.
Yep.
And that forces us to reach the conclusion that the new C will actually be 1/2 of the old C, the same result we got last time, in other words. But the difference in this case is since the Q can't change and the V can, we actually are going to get a different ultimate result. So now I use the definition of capacitance, which is C equals Q over V.
Yep.
And I solve that for V, and I see V is equal to Q over C.
Yep.
So V0, which is the voltage the original capacitor had, is equal to Q0, which is the same thing as Q, because that's not going to change at all, but it's Q0 divided by C0.
Yeah, so Q stays the same. So V equal Q0 over C. And
and therefore V is equal to Q0 over 1/2 C0, which is 2 Q0 over C0, which is of course 2 V0. Does that make sense?
Yes, I can see that.
Okay. So we've established that, and we've established that. So now all I have to use is U is equal to 1/2 CV squared. There's the 1/2. Now I've got to use 1/2 C0 for Z. So that's what that is. And I've got to use 2V0 for V. That's what that is. Of course, when I square the 2, it becomes this 4 right here. And this 1/2 times this 1/2 makes it 1/4. So that 4 cancels out this 4, and I'm just left with C0 V0 squared.
Oh,
So now if I take the new U and divide it by the old U, I get C0 V0 squared over 1/2 that much. So it's just 1 over 1/2, which is 2. Did that make sense?
uh, wait, I'm writing them down so I can like maybe better understand them.
Yeah, it's pretty tricky. You're doing good keeping up with it. This is a more advanced problem to work it out symbolically like that.
I've always been bad at those type of questions.
They're good. I mean, they really help you understand the physics behind it because, in this connection, you see that when you disconnect it from the battery, you're actually causing the energy of the capacitor to go up by spreading it. Whereas when you actually spread the plates of the capacitor while the battery's connected, you actually make the energy smaller. In fact, 1/2 as big in the first case, and then the first case of the problem we were solving. And then in the second case of the problem we were solving, we saw that the new energy is twice the old energy. You have anything else? Because it's about time for me to go catch supper, man.
There's EFG, but like maybe I can do them by myself.
Okay. What are the other parts? You want to show them to me real quick and maybe I can give you some advice?
Okay, so let me share my screen.
No problem.
So the parallel plate has an area and a plate separation D, and it's charged to voltage V. Use the formulas from the problem introduction to obtain the formula for the energy U at the capacitor. Wait. And find the energy density of.
So they want it in terms of A, D, and V. Do you know an energy formula that involves V at least? There's 2 versions.
Yes, the energy formula is 1/2 times CV square.
That's
and
one of them, yes. And what's the other one with the V in it?
1/2 Q times V.
Okay, that's right. Now, this one, they're actually telling you they're going to, they want it in terms of the area of the capacitor and the separation of the capacitor. So that tells you you need the one that not only has a V in it, but also has C in it. So now you're left with exactly one equation you can use. Which one's that?
1/2 CV square.
Exactly. But instead of C, you're going to put epsilon 0 A over D, right?
Yes, because it's asking for the parallel plate cap.
Yep.
So the formula I'm using is 1/2 sigma naught A over D for the first one. So part
Okay.
F is asking for a parallel plate capacitor has an area and a plate separation D, and it is charged so that the electric field inside is E. Use the formula from the problem introduction to find the energy U.
Okay. So this one, notice it doesn't have a V, but it does have a E, the electric field strength.
Uh-huh.
It also
So-
has the A and D. So the stuff we were using in the original equation is fine, the 1/2 CV squared, because
Yep.
that'll allow us to use epsilon 0, A and D. But there's an equation that tells us what the voltage is in terms of the electric field. Do you remember that equation?
Is it? Wait, can you repeat that? Oh, wait, is it electric
Yeah, we're
field is
wanting the
equal?
voltage in terms of the electric field for a parallel plate capacitor.
Is it E equal to negative V over D?
Yeah, except you can ditch the negative. I would normally say V, the voltage, is equal to the electric field strength times the D, the separation. So you're doing the exact same thing that you'd had in part E up there, except now you're going to replace the V that was squared with E times D in parentheses squared.
So
Does that
the
make
formula,
sense?
okay, so the formula will be 1/2 C times E times D squared.
Exactly, but the E and D are both in parentheses, so both of those will become squared.
Yep.
Okay. All right. Well, is that good enough to get you going, bud? Because I got to split.
Find the energy density U of the electric field in the parallel plate.
Oh, I see. There's a part G.
Yep.
The magnitude of the electric field inside the capacitor is E. Okay. So what they're wanting you to do is take that energy that you found in the previous one, and you're going to divide it by the volume in the parallel plate capacitor. Now, the volume is actually the area times D.
Volume is area times D.
Yep.
And wait, that's it?
Yeah, so now you're going to take that U that you got in part F, and you're just going to divide it by A times D, and a lot of cancellations are going to occur, and you're going to get another equation that I gave you yesterday in class.
Wait, so in part F we found, oh, so we used what we found in part F into part G,
Yep, and just divide it by A times D.
divided by A times D. Okay,
Because A times D is the volume of the electric field between the plates.
okay, I think I got,
All right,
okay, I think I can figure it out. Thank you, Professor.
no problem. You have a good one, Mark.
Thank you. Have a good
Bye-bye.
day.
You too.